I am flipping a fair coin. Question for you now, viewer. I have already flipped 6 heads in a row. What is more likely to happen when I flip the coin again? Is it A, heads, B, tails, or C, they both have the same chance? The chance of flipping either side is always 50%. At least, that is what we are all told growing up. What if I told you that that's not the case? Stick around to find out. Whenever we flip a coin, we have what's called a moving average. That is, the average of our flips changes each time. It's moving. Think of it this way, let heads equal 1 and tails equal -1. Whenever we flip a coin, our average will represent the average of our total flips over time. For example, if we flip heads, our average is 1, and tails, then our average is 0. And another tails, our average is now -1/3. This is where another term comes into play, the law of averages, which states that most future events are likely to balance any past deviation from a presumed average. This comes from statistics, which is why we get words like deviation in the definition. Therefore, we can conclude that this definition means business. Going back to our original problem of 6 heads in a row, the law of averages states that our next flip is likely to be tails so as to balance out this moving average and bring it back to 0. But can we quantify this statement? That is, what is the exact probability that the next flip will be tails? I mean, we know it's greater than 50%, but by how much? It turns out that we can calculate the exact chance by using what's known as a normal distribution with this fancy formula. I mean, look at that thing. It looks fancy because it is fancy, and we can therefore trust it completely. When I move the C slider, you can see the purple dot move along, bringing the shaded green region with it. In this example, the shaded region shows the probability of getting tails. As you can see, when I roll heads, the purple dot moves right, making the shaded region bigger. If we look at the fancy looking integral expression, we can find the value evaluates the area of the shaded region, also known as the probability of tails. We can do this because if we just scroll up, the area under the green curve is 1. But how much do we move the purple slider each time we get heads? We use this incredibly fancy and applicable sigma, with n being the total number of heads in a row we get. For example, when we have n as 0, we rolled nothing, so it makes sense to move the slider over 0. But if we roll 1 head in a row, move the slider over 1/2, then 0.75, then 0.875. Also, you may be wondering, where did that 1/2 come from? Well, it's simple really. How many sides are there to a coin? 2. That's right. What's the number right there? 2. That's right. Before starting your flips, what's the chance of rolling heads? 1/2. And what's that number right there? That's right. Phew. Now the astute among you may know that this expression will only approach 1 if we roll many heads in a row, and that makes sense. If we put the slider to 1, meaning we've rolled an infinite number of heads in a row, the integral says that the probability of tails is about 84%, which makes sense because there is always a chance to roll another heads. And what if we roll tails? The law of averages is still in effect if we have, let's say, 6 heads and 1 tail. We simply use the sigma equation again. 1 tails in a row sets n to 1, so move the slider in the other direction 0.5. We go to 0.5, which says that the probability of rolling another tails is around 69%. So now we know the exact answer. If we roll 6 heads in a row, it is more likely to roll a tails next, and the exact chance of rolling tails is about 84%. I hope you've learned a lot from this video. I know I have. And up next, watch this video on the left where I win an art contest, surprisingly, and the video on the right where I make a Rickroll in Desmos. Thanks and have a great and playful rest of your day.